Good morning again, everyone. Today we are going to continue with texture mapping. This was actually in schedule. This was in week 4. It's actually week 5. We were supposed to finish it last week, but we spent more than 2 hours for data structures for graphics. So we are going to continue with texture mapping this week. And after we finish this, we are going to start talking about modeling transformations. Modeling transformations are, we'll see some matrix-based, linear algebra-based transformation of vertices of objects to have, for example, to move them in different places in your scene more efficiently. And modeling transformations is also an important step in the other algorithm that we're going to be discussing until the rest of the semester, which is the forward rendering pipeline. So so our plan is to start modeling transformation this week, maybe even today, depending on how we go, how fast we can finish these texture mapping slides. All right, texture mapping actually is a really important concept in computer graphics because it provides a lot of realism in the scenes without the cost of without additional too big rendering cost. So instead of assigning colors, so up to now our scenes, we're with the ray tracing algorithm, we're capable of rendering scenes that look like this. We have nice reflections, we have shadows. I mean, shadows and reflections, they provide lots of realism to the scene. I mean, our scenes look really cool with the shadows and reflections. And we have the basic illumination model with diffuse reflection depending on the position of the light source and the interaction with the surface. Also, the specular reflections on the objects. So these are basically, this is how our ray tracing algorithm looks like. Now, here, so this is in the assignment. You used everything we have learned. I mean, you're supposed to use everything we have learned up to now. And now we are going to learn something new, which is going to put more realism into scenes. Because in real life, objects do not have fixed reflectance coefficients all over their surface. If you look at an object, I mean, in your tabletop, there are patterns on it. For example, let's look at this one. So this is a marble table. The marble, for example, does not have the same reflectance coefficient. It doesn't have the same color throughout the surface. So we should not give a constant reflectance coefficient to the entire object. And the change in reflectance coefficient is really something complicated. So we need a mechanism to actually map these reflectance coefficients to different points on the objects, and the best way to do that is to have actually a 2D photograph, a 2D image, which is called a texture. Texture is a texture basically is a 2D image, which we use it as each pixel of this 2D image will be used as reflectance coefficients of surface, or I mean, we can use them differently. We can use them as reflectance coefficients. We can use them directly to completely bypass the basic illumination model and assign whatever color we have here directly on the surface point. So we can use this for several different purposes, but the idea is to have a 2D image. So instead of we need to have lots of reflectance coefficients if you want to give all these different patterns to different points on the surface of an object. So the best way to list those different colors, thousands of colors you want to give to a surface, is to represent those colors because the reflectance coefficient, if you think about what the reflectance coefficient is in our input data set in the first assignment, for example, it was just for each material, we define a material and the material reflectance coefficients are just RGB, are like RGB colors. They are between 0 and 1, but you can easily map them to 0 to 255. They're nothing but just color information. So if we were to give many such colors to the surface, the best way to represent them is as a 2D image. So that's what a 2D texture is. There are different ways to have textures. There are procedural textures, for example, in which you assign different colors to the surface based on some kind of a pattern rule. For example, if you want to have a checkerboard with black and white colors alternating on the checkerboard, you don't need to have a 2D image for that. Okay, it's just either black or white, just depending on your pixels, coordinate on the surface. You would either give black or white reflectance coefficient, and you can have a procedure to do that. Even more complicated patterns than checkerboards could be done procedurally. So there are procedural textures, or there are textures that are like images. This marble image here is one such texture, or it may be artist drawings drawn by hand. And the easiest way to provide realism, for example, if you want for example, to a virtual town with lots of buildings, is just to take your photograph, take your camera, and take photographs of these buildings around in the real world, and have those 2D images mapped onto your virtual building's large rectangular sides. So it will provide an immediate way of realism to the virtual scene, because you have those real pictures, real photographs that are mapped onto these virtual objects. So it's a really nice trick to provide additional realism to scenes. So it's a cheap way and a very effective way, and GPUs have actually dedicated texture memories in which you can upload, you can use those memory locations specifically for texture mapping. And there are different issues in texture mapping, like what should be the resolution of the image. Maybe we can, just like we have multiple resolutions of geometry, from low polygon models to very high polygon models, we can have something similar with textures. If for an object that is very far away, or for an object that is very small, why do we really need to use a really high resolution texture? A lower resolution version of the same texture could be used. So there is a concept called MIP maps, MIP mapping, MIP map, which actually is used to create a hierarchical levels of resolution for a 2D image, 2D texture, and selecting automatically out of the best resolution texture depending on the size of object that is projected onto your image. So we are going to learn more about these MIP maps, for example, when we come to OpenGL. These things are supported by OpenGL. OpenGL supports texture mapping, but even in your ray tracing algorithm, you may easily extend your ray tracing first assignment to handle texture mapping. We are going to see how we are going to do that today. So it's So image texture size and object sizes may vary. So we need some kind of a systematic way. So this uniform way also is saying the same thing as you need a systematic way to have a 2D texture image mapped onto the geometry of the objects. And we also need to have a systematic way. So for example, this is interesting. We have a sphere here. If we have a 2D texture image, how can you map? So look at this one. We had this world map or image is 2D. But on the other hand, the sphere is, is 3D. I mean, we could have a 3D rectangle here, but it's spherical. I mean, how can you make a one-to-one mapping between something here and something, a sphere like this? The idea is Basically, although this is a sphere, these objects have surfaces which are like two-dimensional manifolds. For example, any position, I mean, on the surface of the Earth, I mean, this is like, I mean, if you're standing here, it's like flat. So a reference to flat earthers here. The Earth actually is not spherical like this, but it's possible to have a flat texture like this to be mapped onto a spherical Earth because the surface of the Earth, any point on the surface of the Earth, could be identified by two-dimensional coordinates. And we use that today. I mean, the latitude and longitude based on, so that we have a coordinate system for the surface of the Earth, ignoring the height of buildings and, I mean, ignoring your third coordinate, your height in the third dimension. A location on the surface of the Earth can be represented by two values, two coordinates, which make this a two-dimensional surface actually. So this image is also two-dimensional, although it's rectangular, it's two-dimensional. If we can provide a mapping between the surface point and a pixel here, and the image texture coordinates are usually given in this UV coordinate space, or sometimes ST. You may also see that we may be using ST coordinate system to indicate the texture coordinates, but sometimes it's UV. Okay, so don't get surprised if you see texture coordinates are represented by ST. But in any case, the whole texture image to provide a uniform coordinate system. The entire texture actually ranges from 0 to 1 in the x-axis and 0 to 1 in the y-axis. Sometimes this y-axis can be inverted, as in this example. As you can see, the v coordinate axis goes down. So it's like just like in images, you first write in the file. You first write the first row, second row, third row. Just like that, we may have the coordinates increasing from top to bottom of the image. But in some texture images, the coordinates may be actually like this. Here it may be U, this may be V. Okay, so depending on how you define the texture coordinates, the coordinate system may be defined differently from system to system. But just know that, but the important thing here is that the image itself has a two-dimensional coordinate system. And as a standard, the entire image, although it's a rectangular image like this, the texture coordinates range from 0 to 1, from the left end of the image to the right end of the image, and 0 to 1 to the top to the bottom of the image, or bottom to top, vice versa. But it's 0, the texture coordinates are given between 0 and 1. So if we have a texture coordinate, our goal will be, for example, or let's look at this problem. I'm going to render a sphere. Let me just let me just now go to GIMP here. So here's the problem. It's not that difficult actually. Texture mapping is a simpler mathematical problem. So we have a sphere here, okay? So let me try to make it like three-dimensional. Okay, so we have a sphere here. The question that we try to answer is that, and we have an image, an image of the world, for example. Again, this may be V, this may be U here, and 0, 0 here, and 1, 1 here. So this is our texture image, and we can, it's a continuous, it's a real valued coordinate system, but depending on what the UV coordinate is, we can find the closest pixel to this UV coordinate, and we are going to see different techniques in that. For example, if your UV coordinate happens to be somewhere somewhere here, are you going to be selecting the closest pixel, or take the average of pixel values that are closest to this one. Maybe take the average of the 4 pixel values that are closest to this one. So there are different approaches. There's the closest pixel, there's bilinear interpolation. Bilinear interpolation is basically an interpolation based on how close the UV coordinate is to these 4 pixels around it. It takes into account the distance from this point, UV point, to the center of each pixel that is surrounding it. So we are going to see these techniques today. But the question that we try to ask is this. I have an XY point. So imagine we are doing our ray tracing, XYZ. Okay. We are doing our ray tracing and our ray hits this point. Okay, we have the coordinate of the XYZ point. We know that it's a sphere. We know its center, for example. Now, which reflectance coefficient are we going to use for this XYZ point? So that's we need a mapping, we need a function which gets this XYZ and returns some kind of a UV or SD coordinate. If we have such a function which takes these XYZ coordinates on the sphere as input and gives us back a UV coordinate on this texture image, we will just use this as a lookup table. Okay, so for a different ray at a different XYZ location, we will call this function, or we will do this mapping, table lookup or function, whatever you want to refer to it as, and it will give us a when we get this 2D coordinate of a texture, then we just do a lookup on our texture image in this SD coordinates or closest SD coordinates. So one thing we could do is, for example, a very simple approach is whatever these UV values are, if you know the resolution of your image, for example, if it's a 1000 by 2000 texture image, and for example, you have this, for example, the U coordinates, UV coordinate happens to be 0.45 and 0. For example, 36. This is your UV coordinate. Which pixel, and let's get the closest pixel to this 0.45, 0.36. So what we're going to do is, if this is between 0 and 1, this 0.45 corresponds to, if you multiply it by 2000, it's going to be 900, right? Yeah, it's going to be somewhere, the pixel 900, so we can just, it's an integer, so we don't need to, I mean, if it's not an integer, we may round it, so it turns out to be integer, so 900. So multiply this by 1000, it's going to be 360. So the pixel coordinate 900 and 360. So just whatever RGB value we have in this pixel, just grab that and make it the reflectance coefficient of this value. Now the question is, how do we construct this mapping? Actually, we are going to define the mapping ourselves. Let's assume, because this mapping can be done in many different ways, depending on how you want this picture to be mapped onto this earth. For example, we want the best way to do is, for example, I mean, if you're going to proceed with this, the best way to proceed is, for example, I already told you that the surface of the earth is actually two-dimensional. It's a two-dimensional manifold. So why don't we convert these XYZ coordinates to two values like latitude and longitude? For example, if this is if I'm going to assume that this part of the earth, although it's not the 0 latitude, but I'm going to assume this is 0 and I'm going to map it to here. Okay, so this column here is going to map to this location, and as I go along this sphere in this direction, I'm going to, for each angle, I'm going to, so in other words, the 360 degree angle from starting from here and going all the way around, okay, 360 degrees, is going to map to 0 and 1 here. So it's, in other words, 0 to 360 degrees for the columns, okay? And for a point here, the goal will be, okay, it's given this XYZ point, can you find the angle it makes with this center 0 degree angle? So we are going to find a couple of, the other angle is, which actually changes from minus 90. So this is minus 90, this is 90 degrees. The other angle is it makes with the equator, or it makes with this XY plane. So how high above we are from the equator. So if we're at the North Pole, the angle will be 90 degrees. And if we're in the South Pole, the angle will be minus 90 degrees. So from minus 90 to 90, this will indicate where we are. So just like, it will be just like latitude. And the other angle is just longitude. And there's actually a way to do that. There is a parametric representation of the sphere. So this XYZ, if we were to use a parametric equation for a sphere, the parametric equation of a sphere actually has two variables, two parameters, just like a parametric line equation has one parameter. Parameter sphere equation has two parameters, in which, let me just show you that directly. So this is the parametric sphere equation. Look at these XYZ values. So yeah, this slide is all about how we can parameterize the surface of the sphere using two coordinates, because it's a two-dimensional manifold. So it looks very much like the figure that I drew on GIMP. So given an XYZ point, there are two angles that uniquely identify this point's location on the sphere. Let's call these angles theta and phi, which are defined like this. If you look at this image, theta actually is defined differently than the angle that I defined here. Theta is that, like, similar to latitude, but it is 0 when we are at the North Pole. Look at how theta is defined. So given this point, we can, so this is r. We know that this is r because any point on the sphere is r distance away from the center. Okay, so this hypotenuse is r, and so this angle, which is 90 minus theta, gives us its projection here. And it's also, so this angle here is defined as the phi. So the 0 degree is like Greenwich is somewhere here, the 0 degree longitude. And the angle phi is defined in such a way that it ranges from 360 degrees from minus pi to, so phi ranges between minus pi to pi. So this is where it's minus pi, this is 0, this is where it's pi. So it's actually defined like the positive angle in the clockwise direction from here. So depending on how you define these angles, you may have different equations, okay? There is no unique way to define these angles. For example, I could have easily defined my theta to be the angle it makes with the xy plane, and in that case it will not range from 0 to pi, but it will range from minus pi over 2 to pi over 2. Okay, so you can just change these parameters, define those parameters any way you like. But this is just one of those representations, one of many possible representations. And here, if you look at the xyz coordinate, our xyz coordinate can be written in terms of the radius and these parameters theta and phi. So given a theta and phi, so this is a parametric representation of a sphere. So given two parameters, you're able to generate all the points on the sphere by changing these parameters from 0 to pi and minus pi to pi. And the good thing is that if you know the coordinates, I mean, the equations on this slide have everything you need to map those texture coordinate to XYZ coordinates to a texture coordinate. For example, the F function that I mentioned on GIMP, it's actually here. It's represented here. So given an XYZ coordinate, what we do is we divide the Z coordinate of the point by the X coordinate, and the arctangent of that gives me this angle phi. So that's the phi angle. Phi changes between minus pi and pi, so you can linearly map minus pi to 0, the coordinates, the v coordinates. Actually pi correspond to the u coordinates, right? I'm sorry, phi correspond to the u coordinates, really. Yeah, so this is like the columns of your texture map. As phi changes from minus pi to pi, the v coordinate on the texture image is going to be changing from 0 to 1. So you can also map whatever this arctangent returns. You can just again linearly map it to 0 and 1 to find your v coordinate. And this is how you get the phi value. The theta value is just given by, if you divide your y coordinate by r, so the ratio of y with r gives you your theta value, and this is how you map it between 0 and pi. So there's one thing interesting here. There is at the poles there is degeneracy, right? I mean, many of the points, for example, even if I mean it will have there will be actually one x coordinate here at the North Pole, but what I'm trying to say is that if you look at this image, the entire first row and the entire bottom row maps to a single point on the sphere. That's the degeneracy. But it doesn't matter. It will just give us, I mean, if we have the point here, whatever, we will know that it's the first row. And if you look at the world map image here, the degeneracy is actually handled out by giving probably a single color. The entire row probably, so it's like the north and south pole are stretched out as the single color is stretched out as a color value for the entire row. The stretching actually occurs all over. I mean, the level of stretching changes, but it's the same thing here. Many of the rows here, there is no linear mapping between the number of color values here to the number of points they map to on the sphere. But still, we are able to provide this mapping, this function f, to given an xyz coordinate. All you need to do is in your ray tracing algorithm, you have the xyz intersection point of a sphere, right? Just compute this theta and phi values by using these equations. These come from the parametric equation of the sphere, and then map these to 0, 1 texture coordinates. Multiply those texture coordinates by the resolution of your image to get your pixel coordinates, or sometimes they're called texels, texture element, and it will give you a reflectance coefficient. And if you do that, you will immediately get a picture that looks like this. Where do we have it? Yeah, you can do this enhancement easily in your ray tracing codes to have a world map to your sphere, and your sphere is going to look like this easily. Okay, now let's talk about the other stuff. For example, how do we get the pixel values? Do we get the closest one, or by do we get the 4 closest? Do we average linear by some interpolation the 4 closest pixel values, texel values, in order to find this reflectance coefficient? That's the next thing we are going to do. So this is our image. Basically, this equation also shows how you can map from minus pi to pi. So in order to get the value of u between 0 and 1, this is the mapping that I mentioned, the linear mapping of the angle value, the phi value. Phi is actually between, so it's between minus pi and pi, which means that it has a range of 2 pi. So you just add to that pi, which will make it always positive. You divide it by 2 pi. This value will always be between 0 and 1. So this is how you get your u coordinate. And the other one was between 0 and pi anyway. So if you look at what theta is, the range of theta, theta is between 0 and pi. To make it between 0 and 1, all you need to do is divide it by pi, and its range is now between 0 and 1. So this is how this is one way to map a point on your sphere to, or in other words, to assign a texture coordinate to a map on your sphere. How do we do it for triangles is what we're going to also see today. But triangles is easier. It's everything in triangles will be about interpolation. Here, somebody is going to give us a one-to-one mapping between triangles vertices to texture coordinates on this image. So the texture coordinates for the triangle's vertices will be given. And how do we determine those is by in these modeling programs like Blender or 3D Studio Max. When you're modeling your virtual object, one thing that you can do is this: you can either dress a texture on a model by using again tools in the modeling program, or you can paint a texture. One way to do is you can actually paint a texture on the model by brushing tools or other things yourself, and those tools like Blender, they will automatically uh, have a separate texture image after whatever you dress on that model, or whether you paint the texture. They establish a 2D image alongside with your model, and they do this vertex texture pixel assignment of texture coordinates to vertices of your triangles automatically. Yeah, this is also called unwrapping of the UV. So the UV coordinates on the texture, it's like when you already have painted them on your texture. The other thing is you unwrap your model to appear as if it's a 2D image. So this is, as your friend Mujella mentioned, this is called UV unwrapping. There are techniques to do this assignment, UV texture assignment, texture coordinate assignment from the painted textures that you directly paint on your models. But in this course, we're just going to assume that this is what we get with the models. These will be input to our code. We are not going to, this is not a modeling course. We will not go into details on how to do texture mapping ourselves. The texture mapping will be, we'll take it as input from our models. When we download a model from TurboSquid or from some other public repository, we are going to have a texture image alongside with that. Actually, let me show you one. I think I found so I showed you this TurboSquid models. So search 3D models. I just wanted let me log in, download some model and show you how the texture image looks like and the texture coordinates within the model. So here I had this Marty model from Madagascar. Do we have it? Yeah, look at this one. So it was done in Blender and it's free. So I think we are going to. I had this Marty model in the previous years. Now let me download this. As you can see, it's texture mapped. So let's download this one. It's done in Blender. So okay, so I have downloaded it. Let me extract. All right, where is Marty? Right here. So it's Blender. So I need Blender too. So actually in this Blender file, the geometry and its texture image, everything is stored together in this bundle. Maybe this Mesh Lab is able to open Blender files. I'm not sure. Let's see. So what we need is the modeling program Blender to open this. But when I say import mesh, I wonder whether this is able to. No, I don't think it can open. So I need to download Blender to do that. All files. So it can, or you can find a converter on the web easily. From Blender to Polygon, but you can try it yourself. Try to download some model from TurboSquid And yeah, if you click on this, you see there are different versions of it. So this is the geometry. You can see the number of it's a quad-based model. This is and you can see it's really low polygon model. If you use this shading model, which you give fixed normals to all of these polygons, it's a really low polygon model. But if you render it with the texture on and with averaged vertex normals, it looks like a really nice smooth model. Okay, so it looks like a really smooth model. So this is in this texture map model, we're going to see that there's, although this is really a very complicated object with lots of polygons, there is a single 2D image which contains this entire Marty texture unwrapped as a 2D flat. Actually, I think I have that. I can also show you that one. I have the unwrapped version somewhere here. So let me search for Marty. Yeah, this is the Marty texture in JPEG. So look at this. It looks like an image from a horror movie you're going to be seeing. Yeah, look at, so this is the texture image I was mentioning. And it's arranged in such a way that after the unwrapping, we may waste lots of rectangular image texture spaces. But in order to not to waste this space, they are arranged nicely. It's like playing Tetris. You get this part, put it here. So you just try to put it in an efficient manner. We still have some wasted texture spaces like these white places, but I think it's arranged nicely. And it also makes use of the fact that many animals or human beings, we are symmetric. I mean, Marty is also symmetric too. So do we really, for the two eyes, left and right, do we really need two different images on our texture map? No, we can have a single eye here, which is mapped. So as you can see, the texture mapping may not necessarily be one-to-one. We can have a single eye here mapped to both of the eyes of the Marty. To a single texture part can be mapped to two different geometries. And also the same thing with the toenails or and even its body. It's symmetric too, left and right. Just one for one leg, front legs, back legs. So what is this? Is this the tongue? I'm not sure. I think this is like a tail. So this is the unwrapped Marty. And if you look at, for example, Marty and Rogues txt, so I should have, so this is the data file. So these are the texture, these are the coordinates of the geometry of the vertices. At some point, I have these 2D coordinates. These are the texture coordinates for each of those vertices. As you can see, they are between 0 and 1. These are the UV coordinates. For triangles, these UV coordinates are directly provided for the vertices of the triangles or in vertices of quads, whatever you have. The UV coordinates will be directly provided. So texture mapping would really, it will be really easy for triangles or quads actually. All we need to do is, so here's the thing. So we have a triangle. So we know the coordinates of each vertex like this. Sorry, U1 this is going to be U2 and V2 and U3 V3. So this is U. So the vertex texture coordinates are already given. Now the question we will be asking is, if I have a ray, or if I want to know the reflectance coefficient of a point inside the triangle, if I now give you this XYZ, can you find its UV values? Any suggestions on how we can do that? Given the vertices coordinates. We also know their coordinates too. For example, this is x2, y2, z2, and this is x1, y1, z1. So if we have these things, and we have u2, v2, the texture coordinates, given an arbitrary point, which we know is inside this triangle, the question will be how to find its UV coordinates. That's what we need to solve if you want to do texture mapping for triangles. Or we can do it a similar method for rectangles too. But any ideas on how we can do this? Find these UV coordinates from these. One hint. The barycentric coordinates. We have talked about barycentric coordinates, right? When we were talking about the ray triangle intersection, the barycentric coordinates of a point inside. If you remember this XYZ is like a, in the barycentric coordinates case, this XYZ point inside the triangle is actually a weighted average of these three coordinates. For example, vertex 1 plus, this V is going to, we will confuse it. So let's name the vertices of this triangle as P1, P2, P1, P2, P3. So P1, P2 plus P3. So this is this XYZ coordinate. So its XYZ coordinate can be written as the weighted average of the XYZ coordinates of the vertices. So now if we knew these alpha, beta, and gamma, we can actually use the exact same alpha, beta, and gamma on the UV coordinates. So if instead of the geometric coordinates, if we apply the same alpha, beta, gamma to u1, v1, u2, v2, this is how we will get the UV coordinates, as it will be like a interpolation, linear interpolation of these three UV values. But the challenge will be, given the coordinates P1, P2, P3, how can we, and XYZ, how do we find alpha, beta, gamma? And you also know a way to do that, right? For example, you can compute the areas, the ratio of the areas to the area of the triangle. We can find barycentric coordinates easily. It's something doable. You have to work out the math on paper. We have to see it, but we have a method to find the area of a triangle given the coordinates of its three vertices. Or we can use this method that does this for any polygon, right? So we have the triangle's coordinates. We can find the area of the triangle. You can do it by either using cross product, because the cross product gives the area of the triangle, or you can do this polygon area finding thing, the shoelace formula. You can apply the shoelace formula for the triangle. There is also the half perimeter formula. I think it's similar to the shoelace formula. It's probably they may be derived from each other. But in any case, we can find, given P1, P2, P3, and XYZ, so this is also given, we can find alpha, beta, and gamma as the ratio of these areas, A1 over, for example, A1 over the entire area gives me the weight for V, this one, for P2. So it will give me beta. So beta here is going to be, if I call this area A1, it's going to be A1 over the entire area. So then I can find these. After I find alpha, beta, and gamma, since they have to add up to 1, I need to find only 2 of them. The other will be just this. For example, if you find alpha and beta, gamma will just be 1 minus alpha minus beta. So actually it's a two-dimensional, it has 2 degrees of freedom. It is a two-dimensional surface. And after we find alpha, beta, gamma, we find UV. After UV, after you have the UV coordinates for this point, the rest is the same. You map this UV values between 0 and 1 to pixel coordinates by multiplying them with nx and ny. Whatever the resolution of your texture image is, you multiply them and it will directly give you the pixel coordinate. And the pixel coordinates may not always be integers. Sometimes you will end up with a pixel coordinate that looks something like this: 365.3 and 200.8, for example. Okay, so this may be your pixel coordinate. So which pixel value on your texture map are you going to get for this one? I'm going to get your questions. And we are going to see, from one thing, for example, we can round it to the nearest integer, which will give you 365 and 201. Okay, if you round it to the nearest integers, you can get it. So this is called the nearest neighbor texture mapping. Another thing to do is, let's see where this falls into. Okay, for example, this is 365.3. So this may be that 365.3, and we may look at its neighbors. Actually, I need to draw it here, 0.8, and this is like pixel 200, 201, 364, and 365 maybe. So we are going to look at the 4 closest neighbors. I'm going to talk about that too, and do a linear combination of the 4 closest neighbors instead of just using the nearest one. How do we calculate UV? When we have alpha, beta, gamma, we just apply that alpha, beta, gamma to U1, V1, and U2, V2, and U3, V3. Just like the coordinate itself is given as a weighted average of the coordinates, we will have, these UV coordinates will be just like 2D coordinates that are given to us. We will just use this alpha, beta, and gamma to U1, U2, and to these texture coordinates to get the UV coordinate of the vertex. We are going to treat them as if they are vertex coordinates. So yeah, depending on how they actually map, if these UV values for these vertices are given to us not geometrically equidistant in the triangle, it may have an effect of stretching the triangle's texture image, actually. But it's the responsibility of whoever is the modeler of this texture, whoever is doing the modeling, doing the texture mapping on Blender or 3D Studio Max. They need to make sure that geometrically these UV coordinates map to triangles of similar sizes or so. Okay, so if that's the case, the UV coordinate will simply be a weighted average of alpha, beta, gamma. All right, so actually we've covered almost everything about texture mapping, but there are still some parts that we haven't covered. Let me go back to the slides, and we will come to this triangle texture mapping later. But the idea is basically to find that function f. Okay, in all of these texture mapping problems, we have a coordinate here, x, y, z, that a point in ray tracing, for example, this is the point where our ray intersects with the object. It may be a sphere, it may be a triangle. And our goal is to provide a mapping to some UV coordinates in the texture map space. And this can be done by either parameterizing your surface procedurally and finding these 2 values that you're looking for from this. And it's really important how you compute this theta and phi values, because imagine you want to rotate your sphere. When you rotate the sphere in your ray tracing image, since the sphere really is symmetric, if it's not texture map, you will not see any difference, and you will not see that it's rotating. For example, when it's rotating around the y-axis. Imagine you're rotating your sphere around an axis that is parallel to the y-axis and passing through its center. So imagine we are rotating the sphere this way. We want to provide an animation of a rotating sphere. Now, When you're rotating the sphere, this xyz coordinate here, I mean, the sphere's equation doesn't change, right? I mean, let's see what happens when you rotate your sphere. Its center is this, its radius is this. So when you find a point xyz on the sphere, your equation of your sphere, its center, then you're rotating, its center doesn't change, its radius doesn't change too, so you're not scaling it. So you're always finding, when you're, even if you're rotating your sphere, this point xyz, it's not going to come here, it will still be the xyz here. So if you're computing the angle, what I mean for a point here xyz, even if you're rotating it, you're always going to get the same phi and theta angles, which means that even if a texture map sphere, we will not see the effect of rotation if you compute the angle with respect to this major x, y axes like this. So, which tells us, I mean, which basically forces us to use a different representation for a sphere, not maybe just its center and radius. What if we also have, we store with like a local x coordinate, local orientation of a sphere. So when we rotate the sphere, this local orientation vector is also going to change, and this local orientation could be given in multiple angles. For example, we can give where its equator is looking at, we can also give where its north pole is looking at. There may be two vectors we store. So it's like storing a local coordinate system along with the sphere. And when we rotate the sphere along its center axis like this, what happens is that this representation of the sphere changes. This vector, which was 1, 0, 0 before, it will be something else. It will be maybe, for example, 0.6, 0, and 0.8. Look at this vector. Now, it was 1, 0, 0 before, pointing this way. Now it's 0, 6, 0, 0, 8. It's still 1. But if I compute the angle phi, not with respect to the x-axis, but with respect to this local reference direction that I have for the sphere, now phi is going to change for a point here, right? So this is how you can actually model the rotating textures on a sphere. So we are going to see modeling transformations. You're only going to see them for vertices, for polygonal objects, but just this was just a side note, side information. If you were to have your texture mapping, if you want to expand your ray tracing algorithm to have this texture map images onto the spheres, the way you implement it right now, your textures will not be able to rotate around themselves. Okay, I mean, the sphere is just going to remain as if there's no rotation on it. Okay, now we can have a break now, okay, before we go into the interpolation strategy. When we have the texel coordinates, which may not be an integer necessarily, when we multiply those UV values by the texture resolution, we may get values like this, 365.3 and 200.8. How can we turn these values to actual integer coordinates? So this is the simplest one is this one. You just round them, get the nearest integers. That's your texel coordinate. This is called the nearest neighbor approach. The bilinear interpolation approach is a little bit more complicated. Let's continue talk about this after the break. Okay, so I'm going to stop recording now.